After in here. Okay, and so let's see, where does I want to go here? Oh my gosh, last time we finished off, we talked about impact parameters last time. Remember that?
Yeah.
And so now what I want to do is I want to focus on using conservation of angular momentum. And at the risk of boring you a little bit, let's do this. Make sure I get black pen. Actually going to come over here just a little bit. Hopefully that's still on screen, just barely. So what we want to use is L initial equals L final. L being the symbol for angular momentum. And in particular, we need to check, is it okay to use? Does anyone remember the condition that has to be true if we want to be able to use conservation of angular momentum? Something had to be negligible or zero. Do you remember what it was? The sum of, what was it? External torque has to be either zero or approximately zero in order for this to be useful. All right. For most objects, L is going to be I omega, but then we might need to think about plus and minus signs here, right? If something's rotating in the positive or negative direction. And then finally, the trick we used for point particle we're going to use this L equals M V R perpendicular, where R perpendicular was the impact parameter. Got it? And then, yeah, so hopefully you can see that. I'll zoom a little bit. Is that visible at all or not? Is it a little small, Alan?
The point particle one is.
Let me just do this. It's wrong way. Come on. My gosh, come on. Is that better?
Yeah.
Oops. Gosh, spent so much time on camera in this class. All right. So that's our short summary. We want to use this, and that's not going to mean much until we do some practice problems. And regarding that, the practice problems that we're going to do, maybe I'll just list them now. That way, if we don't get through them all, you know what you could review at home. So 5, 6, 8, 9. So some good problems are going to be 11.5, 6, 8, 9. Let me get a couple more here. 11. 11 and 111, one of my favorites. Yeah, I know, isn't that dumb? And 16.
So does that mean there's 11 after problem 11? Or is it 111?
Maybe the answer is 111, 11 and 111. No, I don't know, yeah. Yeah, there's a problem 11 and then there's a problem 11 and 111. You see it down there?
Yeah.
Yeah. All right. And then actually there's a bunch more problems. Let me just say 18, 19, whatever. I'll talk about that at the end of class. But so these are kind of the main variations of how I might do these problems on a test. So if you need to know the types of tricks I might throw at you on test day, that's all of my tricks. You might not have time to do all of those, but if you do most of these problems, you'll know most of my tricks and you'll start to see the similarities. Got it? So that said, let's try and do as much as we can in here, and then a couple of really fun demos that I've got set up here, and hopefully we can learn something. All right. Let's start with the first one, 11.5. And I think actually, before we start, let's look at it. It's not a perfect example, but I'm going to show you a visual of it. Here it is. Take a look. You got a disc, it's spinning. You drop this on top. You see the rotation rate change a little bit? Watch it again. You see it slows down a little bit? That's the problem we're doing. Got it? Okay, let's do it. This is my attempt to visualize it. I'm going to draw a disc like this. And I'm going to draw an axis of rotation here coming out through the middle. Maybe I'll draw this axis too. I'll call this X. I'll call this X. Let's call this Y. Sorry about that. And up here, this is going to be the Z axis. Now up here, I've got my ring. My attempt to draw that. Just so you can see that it's not solid, I'm going to shade this one in, okay? So the idea again is this is a solid disc, and that ring is a thin ring, okay? So to clarify that, let's go thin ring, has mass capital M, radius R. This is a disc, mass M, radius R. And I believe what did I do? I think I had the disc rotating, right? Now it gets annoying having to say disc and ring all the time. So I'm going to slap some numbers on here. I'm going to call this one object 1 and this one object 2. Is everybody okay? Just so that way we don't have to keep writing the words disc and ring. We can use like 1s and 2s. Okay. So what I could do now is that allows me to say omega 1 initial is equal to, in this problem, it was 10 RPM. Now notice I said RPM, not RPMs. Right? If you think about it, the S is hidden inside the R, right? Revolutions per minute. I'm pretty bad about this. I say RPMs all the time. I say pounds all the time, but it should be RPM. It should be pounds, LB, right? Anyways, got it. Now in this problem, I want to emphasize something just to set you up for success later. If this was a vector, what direction would it be? What is the direction of that initial 10 RPMs? It's rotating this way. Yeah, we would call that K hat. And what happens is, imagine I do another problem where it's rotating the other way, then it might have a negative 10 RPMs or something, right? Or one of them could be positive and the other could be negative. That's a classic problem I've given before. So it's important to understand where the plus minus signs may come from, and it's from this vector quantity, all right? All right, so reading this problem, let's read part A. Just in case we need it, convert 10.0 revolutions per minute for radians per second. Well, I know that's, wait, 1 rev is 2 pi radian, and 1 minute is 60 seconds. Should be approximately a factor of 10, one way or the other. I never remember, but it's about 10. So let's take a look here. I got 10 times 2 times pi div, whoops, 10 times 2 times pi div 60. I got 1.047. I'm going to keep an extra digit just in case. right? That way I'm not intermediate rounding. In this case, I would probably round right here, right? Usually with numbers that start with 1, you usually want to keep an extra sig fig on that. So your number starts with 1, we'd normally keep 4. That's the default. All right. So initially, this thing's rotating at 10 RPM or about 1 radian per second. We're going to drop this thin ring on it. And the thin ring is initially at rest. So we could say that by saying omega 2 initial equals 0. They have the same mass, the same radius. When you drop it on top of there, what do you think should happen to the RPMs? In particular, if you drop that same mass on there, do you think it's going to cut the RPMs in half, cut it by less than half, or cut it by more than half? What's your gut tell you? Is it going to be 5, more than 5, or less than 5 RPM after it falls on there? What do you think? Fun question, right? Rather than trying to think it through, just take your guess right now. What do you think? Less than 5? Okay, so let's find out. Okay, you've made a commitment. Now let's find out you'll remember the right answer. The trick is, what we do is we say L initial, and this time I'm going to do it as a vector, equals L final, just so you can see how the vector shows up. Initially, I would say I have I1 omega 1 initial plus I2 omega 2 initial. And then afterwards, they're going to basically form one object, right? Where they're rotating together. So after the collision, they're both sitting here, stacked on top of each other. It's not a very good picture, but you get the idea. The axis is still the z-axis. What should I write for the angular momentum on the other side? How many terms do you think I should have? 1 term. What's the moment of inertia I should use? Absolutely. Looks kind of like a chapter 9 problem, doesn't it? Where you have a perfectly inelastic collision. This is a perfectly inelastic collision with rotation. Does that make sense? Is everybody cool with that line?
Yeah.
Okay. Zoom in, you good? Hopefully. All right. Okay. I1. It's a disk with mass m and radius r. What moment of inertia is it for a disk with this axis? I believe that was like page 53 or 59. You might want to earmark it. We're going to use it all day today. It was page 59. Just put a page mark on there or something. Put the paper in there. What was it, Alonzo? Yeah, so for the disk, I get a 1/2 m r squared. Omega 1 initial is our known. Let's leave it as omega 1 initial for right now. What was omega 2 initial? The thin ring is initially not rotating.
And r squared.
Oh, true. But what's going to happen to this entire term?
Oh, it's just gonna zero.
Yeah, this one's going to zero out. We need it for the other side though, so you're right.
Yeah.
So what were you saying I2 is? MR squared?
And r squared, yeah.
So we'll use it right there. And we add to it this other 1/2 for the disk. And then we got our omega final here. Got it? What cancels out? What does every term have in it? M. What else? Yeah, in this special problem, they all have the same R and the same M. So basically only the shape factors survive. So now I can rewrite this a little bit more cleanly. I get a 1/2 omega 1 initial is equal to, what's that gonna be, 3/2? And notice omega final equals omega initial over 3. So it cuts it by more than half, right? It cuts it to 1/3 of its initial value. We could say you lose 67% of the rotation, right? 66.6666. That's kind of interesting. At this point, we could plug in our decimal numbers. I will. And just divide that by 3. I got 0.349. Oops. Okay, so I just use this number, plugged it in, divide by 3. How's the pace? Is this too fast or is it okay? Okay for now? And remember, you got the full solutions if I go too fast. Okay. Let me ask you something. Do you think the energy should go up, down, or remain the same here? What do you think about energy? We just did an angular momentum problem. What should be true about the energy? Why? He said it should go down. Why do you think? Well, if it slows down, but the moment of inertia goes up, do you agree? Is it possible the increase in moment of inertia will balance that out? What do you think? It's not obvious. Do you agree? Just because it slows down doesn't mean we know we lose energy. You are correct, though. That's good intuition. I don't want to mess with you too hard here because you're right. Let me ask you this. What type of collision is this? Perfectly inelastic. Do you remember in chapter 9, did perfectly inelastic collisions lose energy or not?
Oh, wait.
Elastic meant E initial equals E final. This is perfectly inelastic.
No.
We lose energy usually. If two things collide and stick together, you almost always lose energy. Why am I stressing this point? On test day, the most common mistake on these types of problems is people try to use conservation of energy when energy is not conserved. If you tried to do this problem with energy, you'd be wrong. And like, basically, that's a trigger for me. It's like automatic 0. Okay, if I see you do conservation of energy on an angular momentum problem, I get so furious, I'm just like 0. I'm just letting you know. More on that in a minute. I'm going to hammer this and try to make sure you don't make that mistake. And I'll show you how as we go through the day. That said, energy is not conserved. Let's see how the energy changes. Let's go to the next board. And I want to show you that. Oh my gosh, actually, let me just do this. Okay, so there's our result. Let me back it up just a bit. Autofocus seems blurry. Okay. So now, percent delta K will equal K final minus K initial, all divided by the initial K times 100%. That's the definition of percent change. It's the change over the initial value times 100%. That's percent change. Got it? Well, we could do this a lot of different ways. I'm going to show you one method that I kind of like. I'm going to rearrange this and just divide through the K initial on each term separately. And that way, it's one less formula I got to plug in, right? Well, now in this case, the formula for K final, what's the formula for kinetic energy final?
1/2 mv squared.
No, that's for translation, 1/2 mv squared. So what's the rotational equivalent? Because do you agree we're rotating now?
Yeah.
Yep. Oh, that's so much better. this. Finally found a marker I like. Okay, now in this case, notice the 1/2 drops, right? What is I final? Do you remember? Do we have it written down somewhere? It's what? 3/2 MR squared, do you agree? So I'm gonna get a 3/2. Let me get out of the way in just a second. That's I final. I initial was what? 1/2 MR squared?
Yep.
This one had an omega initial on it. Now I could just write omega final here, but I'm trying to show you carefully, look what happens right here. If we rewrite omega final as omega initial over 3, what's going to drop out? All of the everything. Isn't that cool? So we're going to get a number out of this, even though we didn't have any numbers in the problem. Isn't that wild? Now we can't forget this -1. That's a big deal. So now I've got to be careful. It's easy to start canceling stuff and screw it up. The 2 cancels, as do the MR squareds, as do the omega initial squared and this one. But remember, this 3 has got to be squared. So these 3's don't cancel. In fact, this is going to be 3/9, which is 1/3. So we get 1/3 minus 1. We get -2/3 times 100%, which is about -67%. We lose 67% of the energy. Is that good? So just from a practical standpoint, I found that it's much easier to plug in everything all algebraically here rather than stick in numbers. Now, if you had numbers, by all means, shove in the numbers. But just from my experience, these problems always work out where you get so much stuff canceling. If you do it algebraically, it's worth it to do it algebraically. Okay. I think that's it for that problem. Is there anything else on there? Okay. Well, now I have a question though. We're doing this thing right here, right? If the energy changes, something had to do work, right? It's got a certain rotation rate, and when you watch it, it slows down. What's doing the work? It's slowing this thing down, right? There's a loss of energy. Something had to do work. What are the forces involved in this problem? When this thing's touching it, what's one force acting on it? Friction. You can hear it. What's another force acting on this object? Always. mg, right? I guess not always if you throw it into space, but yeah, whatever. And then what's the other force that's holding it up? Normal force. Now, do you agree the normal force up and mg down are not going to cause a torque? The friction causes a torque though, right? That's what makes this start spinning. And when you drop it, listen, you can hear the friction cause it to come up to speed. It's very brief. It's, right? Oh, that was a pretty good one. Yeah, whatever. But so when that's coming up to speed, you can hear it. There's a torque due to friction. Wait a minute. If there's torque, doesn't that mean we can't do angular momentum? Why is it still okay to use angular momentum even though there's torque?
Short time.
What's that?
Because it's a short time.
Uh,
No?
that's not why I would want, that's not the best reason. That might be actually true in this case, but that's not why I want to think about it.
Is it because we were thinking about it afterwards?
What's the system here? What's the system? These two objects. Where does the friction occur? So it's internal friction. So just because it causes a torque, it's an internal torque. It does positive torque on the ring, negative torque on the turntable. So that's why it was okay to do angular momentum. There was a torque. It was important. It was substantial. It caused this thing to start spinning, but it's internal to the system. Good? I don't even know what I was talking about. I don't even know what I was asking anymore. What was the question? What was their point?
I think he was trying to prove something.
Okay, yeah. Oh, I guess the main thing I wanted to point out here is that there's torque. That's what causes this thing to come up to speed, but it's internal. That was it. Can you think of any devices in the real world that act like this, where you take one object, like a disc that's spinning, and you put another one on it and allow them to match RPM? Maybe a brake. I was thinking a clutch, right? Something for in a vehicle so that you can have, like, as I don't know, I think about a stick shift, right? And you're stepping on the gosh, it's been a while since I drove a stick shift. That's crazy. The clutch pedal or whatever, right? So you can take the discs in and out of contact with each other, and then you can allow the friction to cause their RPMs to match, and then your drivetrain of your vehicle will actually work. As you can tell, I'm not an expert in auto mechanics, so I'm just trying to give you an idea. If that's cool, great. If I'm making you laugh inside, that's fine too. All right. Let's go to 11.6, okay? 11.6. And then what I would like to do is just work on this board. Is that okay? So I'm going to erase this stuff. Give me a sec. My eraser. There it is. Six. Is this pace okay, or am I going too up tempo, or is it about right? Good enough? Okay. So let's assume we have a planet or a star, I think it was. And we're told that the radius is initially 10 to the 4th kilometers. And then it's rotating. Oh, crap. Yeah, whatever. And we're told that its initial period is 30 days. And then, for some reason, gravity causes this thing to collapse to a much smaller object. And it's going to have some new rotational period. My goal is to figure out the final rotational period of this star after it collapses. The final radius is 3 kilometers. Ignore sig figs, who cares? Okay. This figure is obviously not to scale. For reference, 10 to the 4th kilometers, that's about what? 6,000 miles, I believe, right? 10 kilometer is 6 miles. A 10K is like a 6-mile run. So then 6,000 miles. That's basically about a third bigger than the Earth. This size, 3 kilometers, is about the size of Hancock College. So imagine taking the entire planet and shrinking it down to Allen Hancock College. Yowza. Believe it or not, stars can do this kind of stuff. we're going to make another assumption here. We're going to assume that this star has a uniform mass distribution. That's obviously false, but hopefully it's approximately true, and it will give us a feeling of how a star collapsing might affect its rotation rate. Okay, so we're going to assume incorrectly that the mass is approximately uniform distribution, and we're going to assume object is solid sphere. This is not true, but it's hopefully approximately true, at least to give us a feeling, right, for how this star problem might work. Okay? And to be fair, I know nothing about astronomy either. I know nothing about cars. Basically, I know nothing except how to do this problem. All right? Okay. We're going to ignore air resistance. We're going to ignore things like that. This is in outer space. Hopefully, there's negligible torque, so I'm going to use conservation of angular momentum. What I see is I have a rotating object changing shape. Whenever that happens, try L initial equals L final. The reason I said, oh crap, a minute ago was I meant to do the last problem with vectors and I forgot it. So maybe I'll try to do this one with vectors, right? I'm not going to. Usually you don't worry about vectors. You just say one direction's positive and one direction's negative. So to be clear, let's assume this way is the positive direction. By doing that, we don't have to include the unit vectors. So we don't have to make these vectors if I specify a positive direction. Sort of like projectiles. Remember we'd say what direction is positive and things could be plus or minus? Same thing. Okay. In this case, I only have one object rotating, so I'm going to use I initial. Oh, actually I can, yeah, equals I, oh, whatever. I'm going to use this equation. So notice the moment of inertia is still going to change, and I'm going to account for that this way. All right. And now I want to read the problem. Okay, part A asks us to relate period to angular frequency. And a lot of you probably don't know what angular frequency means. Angular frequency is exactly the same thing as angular speed. What symbol is angular speed? Omega. So angular frequency, notice omega has three different ways to say it. You can say angular velocity and include a unit vector. Angular frequency or angular speed, just say omega. Does anybody remember the relationship that we used 5 weeks ago when we were doing circular motion back then? If you don't, I'll tell it to you. This is not written on your equation sheet, so you got to memorize this or tell yourself to write this down. We use this a lot. I should add it to the equation sheet. I just keep forgetting. It's 2 pi over the period. Got it? One orbit, right? That's 2 pi radians over the time gives you how many radians per second? 2 pi over how many seconds it takes to go 2 pi. Write that down, memorize it, never forget it. Write it down on your test as soon as I hand out your test. Whoa! So here's the fun part. What I want to do now is I want to rewrite this angular momentum equation in terms of period, right? That way I don't have to keep messing around converting these to omegas and second. Oh, that's a pain. So what I want to do is I want to rewrite this equation in terms of the period. What do I get? Well, this is I initial 2 pi over period initial two pi over period final, what drops out? 2 pi. I'm going to rearrange this and solve for period final. That's what I'm looking for in the end. I want to find out the final rotation information, either the period or the angular velocity or whatever you want to call it. Solving this for T final, let's make sure I don't screw this up. You can do it on your paper too. I think it's going to be I final over I initial times the initial period. Make sure I didn't flip something upside down. Final comes up here. Initial comes up here. So this should be final. I think that's right. Is that good? That's part B. Determine the new period. Oh, I guess technically this was the answer to part B. Just write the answer. And then this is part C. We're solving for it. So I apologize there. Part C was solved for the new period. Part B was just write down the equation. I was wrong there. Well, the final period should equal, what's the final moment of inertia? It's a solid sphere. Two-fifths. The initial moment of inertia, it's another solid sphere. The only difference is the radius, right? We're assuming the mass is not changing. It's still a star, just collapsing in. Is this some assumption valid? Probably not perfectly, but maybe approximately. Notice, in this case, a lot of stuff cancels out. Oh, whoops, there's also a period here. The radius final is going to be 10 to the 4th kilometers. The initial radius was, wait, I screwed that up, didn't I? The final is not 10 kilometers. The final is 3. I screwed up. Now notice this is squared and this is squared, so I could actually just factor the squared out and take this quantity and square it, or you could square each one. I like doing it this way because then I can see right away the kilometers are going to drop, so I don't need to worry about that. This period was 30 days, and I believe you get 2.7 times 10 to the minus 6 days. I know I'm off on the Zoom, I'll fix it. Okay. This is kind of an annoying unit. 2.7 microdays. That just sounds funny. How many microdays does it take to blink? I'm going to list my reaction time in microdays. Let's convert that to seconds. There's my calculator. Right. So keep in mind, you can multiply 2.7 microdays one day, approximately 24 hours. 1 hour, 3,600 seconds. if you're wondering why I'm saying approximately, think about leap day, right? Why do we have leap day? It's not perfect, exactly. And so, yeah, let's just do this. They also have leap seconds every once in a while and stuff like this, but let's just focus on this. So 2.7 e negative 6 times 24 times 3600, 0.233. I got quarter of a second, basically. Now, imagine something bigger than this planet shrinking down to the size of this college, and now it's rotating once every quarter or 4 times, between 4 and 5 times a second. That's insane. And yet this kind of stuff is not outrageous in the world of astronomy. These numbers are not that far-fetched. And so if you're interested, you could read about what a pulsar is. But pulsars actually send out these blips of information. You can imagine they're rotating very quickly, and they're sending out radiation all the way around. And what will happen is you can get these, literally, you can tell how fast they're rotating by how often the signal shines straight at Earth. And you can tell it's something not unlike these numbers in certain cases. If that interests you, cool. Doesn't interest me. Part D. I don't want to do part D, but I want to ask you something. Part D just asks, what's the percent change in energy? Or I think it says fractional change. It's basically the same calculation. But before we do it, I want you to think about it. Is the energy change going to be 0? Is it going to be positive, meaning does it have more energy in the final state? Or is it going to be negative? Is there going to be less energy in the final state? What's your gut tell you? More. And what's the thing you're keying in on?
Speeding up.
Yeah, right. If we have a small period, we have a huge RPM. And while this isn't always true, it's almost always true. If something speeds up, usually the energy goes up. If something slows down, usually the energy goes down. The key factor in there, I want to point this out. 1/2 I omega squared. If you double the moment of inertia, the rotation rate gets cut in half, but that's squared. If you cut the moment of inertia in half, the rotation rate gets doubled, and that's squared. So usually whatever happens to omega wins in the equation. Is that okay? Because it's squared. Not always, I can't think of an exception, but there might be some weird cases where this isn't true, and I don't want to think about it too much. But generally speaking, if the RPMs change, you probably have a change in energy. All right, good enough on that? There's another way we could do this. Imagine this is a figure skater with their arms out. When the figure skater brings their arms in, what happens to the figure skater? When they're spinning, speed up. Is anybody in here immune to motion sickness? You don't tend to puke when I spin you at high velocity? I need a volunteer. We're going over here. I just need somebody that's willing to sit on a stool and spin around that won't barf. Anybody? You want to try it out?
How long?
Not long. Not long. So we're going to do a variation on this star problem. Go ahead, and so what I'll do is, I'm going to hold this stool in place. Go ahead and sit facing that way. Face the camera there. Got it? Okay. Then here's 2 masses. There's another one. Yeah. And so now, go ahead and put them down for a second. So the idea is, if you get nauseous, just bring your arms back out, because then you should rotate slower. Got it? All right. So go ahead, hold them out. Keep them out. All right. So now bring your arms in. Whoa, yeah, let's give a round of applause there. You want to try one more? One more?
Yeah.
Yeah, so you gotta be pretty well centered on there, do you agree? Got it? Okay. Arms out, give you a spin, you go the other way. Try it again. Whoa, yeah, let's give another round of applause here. There you go. All right, so the idea on this one, if you want to look at it, the problem describing that, it's basically the same. It's problem 11.7 in the workbook. I'm just bringing my workbook over there. If you were curious and wanted to analyze it, you could do problem 11.7. So we use 7-pound weights. It's not exactly the same. And it turns out when you're on there, it's a lot more dramatic than when you're watching it, right? You really, if you want to try this sometime on the class break, we'll do it. But I go through, whatever. We go through the challenge of, the hard part is for human body, how do you get somebody's moment of inertia? Well, you could view their body as kind of like a cylinder or a plate, right? And then you could view their arms as being rods and point masses, and you could figure out a big complicated moment of inertia formula. We're not going to do that. It's too time consuming, but you can totally get a decent approximation for this. And I kind of walked you through that right there at 11.7. And here's the question I have though. In the last problem, we had a neutron star collapse, or whatever it was. And in that case, what caused the planet, or excuse me, what caused the star to collapse in on itself a minute ago? Gravity. In theory, we could have done that problem with conservation of energy. It turns out it's extremely difficult because you have to use calculus explaining how each particle of the star has a gravitational force with every other particle of the star, and there's a lot of calculus. So we don't want to do, even though you could in theory, this one's a little different though, right? What causes the mass to go inwards here? What force? What's the energy source that moves the masses? It's not gravitational collapse. Do you agree? Yeah, well, what's the ultimate source of energy in my arms? What's that? Yeah, I was going to say breakfast. The bowl full of Snickers and milk that I eat as cereal every morning, right? What you're doing is you're converting chemical energy to do the work to bring these masses in. Now, wait a second. Isn't that causing a torque? It's internal. I'm part of the system, right? Now, and furthermore, if I pull the masses straight in, I'm exerting a force towards the pivot. There's no torque anyways, right? I'm just doing work. So it's not like you're getting something for free, right? When you bring these masses in, you're doing the work that causes you to speed up. And then when you bring them back out, you're doing the work to slow yourself back down. Got it? All right. Now, for fun, I've got another variation here. I need another student. Come over here. This one you can control. You ready? Come on up. All right, so now what we're going to do, I don't want to screw this up, so I'm going to try and explain it. Go ahead and I'll give you a. Are you well situated? Yeah. Okay, then put 1 foot on the ground for right now. Just keep yourself. So what I want to do, I want you to hold this for me for a second. Got it? And then I've got this. I'm going to give this some large angular momentum. I need to see what happens. Okay, do you agree it's going to be spinning upwards? Rotate, hold on, rotate this way so they can see you. Okay, so what's going to happen is I'm going to put the Dremel on here and cause this thing to spin this way. Got it? Now, once that's spinning, I want him to rotate the entire apparatus like this. Now, I just forgot which way it was spinning. Correct. This way? Oh, thank you. Okay. So the idea is it's spinning around like this, and he's going to do that. So notice he's going to create angular momentum in the positive k hat on the wheel. He's going to exert a torque on the wheel, imparting angular momentum upwards. By Newton's third law, what should happen to him? He torques the wheel and causes the wheel to go this way. What's the wheel going to do to him? He should go that way. So hopefully, let's try this again. If we spin this, and then he does that, he should go that way. Now let's see if this is true, right? Okay, so now, give me a second here. Let's go this way. I like to get this thing going extremely dangerously fast, so don't stick your fingers in there, okay? Ready? Okay, try going the other direction. I totally forgot everything I said. Is he going the way we said he would go?
Yeah.
Good, because I totally forgot all the directions at this point. Now watch this. I'm going to hold you at rest. Keep the disc there. Keep the disc sideways. Now do a double flip all the way over. You get more change because he flipped it from up to down. Now flip it back. Right? That's pretty cool, right? Let's give him a round of applause here. All right, and then you want to do one more for me? Even though this is not the subject of this class, here, let's get this out of the way. And then kind of stare at the camera here. You probably want to do that, right? Switch sides. Oops. What we're going to do, I want you to kind of wrap that around your head 2 times. You want to hold it above the wheel. Is that going to be good? Let me do this one more time. Okay. All apart. Okay, now I'm going to let go. You hold on. And this is usually pretty odd because we don't usually see this. But you might be wondering why you're more stable when you ride a bike when the wheels are spinning versus not spinning. This is basically a thin ring, mr squared, large moment of inertia, high RPMs, a lot of angular momentum. The gravitational force acting down at the center of the wheel
That's so trippy.
causes a torque. The torque is changing the angular momentum, right? And it's causing it to gradually precess and fall over. You see it is slowly falling over? You see it? I gotta be careful to catch this now. Let's try this again. Whereas if I just let go of this right now, it falls over right away. Now the graph, once it's rotating, you've got so much angular momentum. Can you hold it up higher? You can use 2 hands too. I gotta crank hard. Right? What's happening is that gravitational force is causing the torque, which is causing this weird precessional motion. The good news is, this is not on the test. It's really cool. It's really interesting. You can read about precession. We should probably take a break instead. All right. Let's give another round of applause there. Oh my gosh, where are we? Let's see where we're at and make sure it's a good time to take a break.
5:33.
Okay. Yeah, let's go ahead and take our break now. What do you think? Sound good? And then let's do that. That'll give you time to set up the next couple of things. So let's go ahead and take a break. It's on this clock it says 5:34, so let's come back in 10 minutes, all right? What do you think? Should we go for it? Good a time as any? All right. So now I want to handle 11.8. 11.8. There's a rod and there's a point mass. Crucial that you become expert at this type of problem, right? It's just the type of algebra you get used to in this problem is very similar to the algebra on test questions. So all of the problems that you've seen are good examples of test questions. Basically, I just open the book and pick one that I haven't done in a while and throw it on there, right? And then one of the ways I mix it up is this. I assign a mass to this object, and then over here, notice I say the rod has mass 2m, I believe. Is that correct? Yes. And then the length is d. Usually we try to avoid the symbol L for the length of a rod mass because L is angular momentum, and I don't want to get confused with L length and L angular momentum. And basically, the way I mix up test questions is maybe on a test question, I would make this mass M and length 2D, so that the procedure is exactly the same, but the symbols you got to plug in are a little bit different every time. And so it's crucial to pay attention to, is this mass M, is it 2M, is it 3M, is the length D, is it 2D, is it 3D? And I think we were told this information here. Mass M for the lump of clay moves towards a rod, sticks to the rod, which has mass 2m and length d. Collision time is short. And then the rod clay swings up to some maximum angle. So then impact occurs. Stage 2 is just after impact. The rod is probably starting to rotate, but not by much. Do you agree? We're told that the collision time is very short. And so I'm assuming that the rod has not had much time to rotate. But it is rotating upwards at some rate omega, let's say. Usually with the pendulum, we describe the angle as being to the vertical. All right. Part A is talking about conservation of angular momentum. So the question is basically asking, can we use conservation of angular momentum in part A? In particular, what has to be true if we can use conservation of angular momentum? We require what? Sum of something equals 0. Torques external should be approximately 0, right? Well, what are some of the forces that are acting on it? During the impact, here's the rod, here's the ball. Actually, let's draw it just as they just start to touch. What is one force that's acting on the system? Any force. mg of what? The ball or the rod? Okay, the system. Where does the, okay, so there's an mg, wouldn't that be 3 mg? Do you agree there's a total mass of m plus 2m is 3m? Where does that act? Center mass. Is it going to be at the halfway point of the rod?
A little bit down.
A little bit down, because this is bringing it down, right? So there's a force downwards, I'll call 3 mg. Excellent. Is everybody cool with that? Hopefully I'm on the right whiteboard. There's a force downwards, 3 mg. What's another force? Is there a force from the ball on the rod? Does the ball exert a force on the rod? Yes. Does the rod exert a force on the ball? Is that going to cause an external torque?
No.
No, because those are internal. So there's absolutely forces here. We don't need to label them because they're internal. Excellent. It's not that they don't exist. It's not that they don't matter. The ball will exert a torque on the rod, causing it to speed up. The rod will exert a force on the ball, causing it to slow down. And it's just, you know, internal, so it's equal and opposite. Any other forces? If these were the only forces, what would happen to this system? Falls down. Does it fall down? Let's look at it. Maybe you need to see this one. This, right? Look at it. Didn't fall down. Huh. Right? So there's a pivot point up here. The pivot point prevents it from falling down, so there's a force upwards, which I'm going to call Ry. So it's upwards. However, is there another force on it? I'm going to try and do this. I need a meter stick to shatter. Keep breaking shit. Here's one. Watch what happens when I punch the bottom of this meter stick, right? My punch is supposed to simulate the force on the meter stick. In particular, try and watch the top, and let me zoom out just a little bit, just in case. Okay, so I'm going to punch this meter stick. Try to watch what happens to the top. Ready? I'm going to let go of it with this hand right at the right time. Which way did the top of the meter stick go? So, is that the only force that the pivot exerts? What other force is it exerting? This way. The rod, whoops, I was wrong. Let's see. No, in this case, yeah, Rx, what was it, this way? Now, to be clear, depending on where you hit the thing, Rx could point the other way. For example, watch this. If I punch this rod near the top, above the center mass here, I better be careful, right? I want to hit myself in the... When I punch it up high, watch what happens to the top. It goes away. So depending where the ball hits, you could have a force left or right. Usually we just say, pick some direction. If you get a negative answer, who cares? Just flip the arrow. We'll do that in chapter 12 next. But is everybody okay that the pivot point has to exert these forces? Otherwise, the rod will go flying all over the place. Okay. Okay. So now, we require sum of external torques to be 0. Is that going to be true in this picture? Is Rx or Ry going to exert a torque? No. How do you know? I'm going to go another way with you. I'm going to say line of action through pivot, no torque, which is exactly the same as what you're saying. Do you agree? Yeah. What about mg? The line of action doesn't go perfectly through the pivot, but it's pretty freaking close. Do you agree? So that's why I'm saying it's approximately 0. It's not perfect. This is only approximate. But as long as the collision time is short, angular momentum is conserved. At least for this collision, right? Which stages is that? Is that between 1 and 2, or between 2 and 3, or between 1 and 3? Yeah, so what we could say is wait a minute. We're talking about angular momentum, right? That's usually something rotating. I can see that this is something rotating and has angular momentum. What has the angular momentum over here? The point mass. A point mass moving in a straight line. Remember that impact parameter nonsense? You can think of this as curling around. Remember the video simulation I showed of a particle moving in a straight line? It had angular momentum. This is the initial angular momentum. That is the final angular momentum. So it's okay, even though it looks like there's no rotation here. Moral of the story, if you have a collision that results in rotation, do angular momentum. Got it? Collision with rotation, use angular momentum. What about between stage 2 and stage 3? What's the final angular momentum here? When you rise to max height, how fast do you rotate? 0. Is angular momentum the same between stage 2 and stage 3? No. So do not use I'm not even going to write it. Basically, L2 is not equal to L3. Angular momentum is not conserved. Why not? If it's not conserved, there must be external torque. What's causing the external torque? The 3mg, because once you rotate, do you agree that 3mg is causing a lot of torque once it starts swinging upwards? Now, as a physicist, I'm kind of conflicted. In the universe, we say angular momentum is conserved. Here, we see it's not conserved. What gives? For it to be conserved, some other object in the universe must have that lost angular momentum. What is it? We're looking at this system right here. This drove me nuts at first when I was thinking about it. So if you're perplexed, you're not alone. Right now, we see there's angular momentum right after the collision when this thing's swinging upwards, and then it stops. There's no angular momentum. What other object in the universe got that angular momentum? The Earth, the planet. Now keep in mind, is this amount of angular momentum going to change the Earth's rotation rate much? No, right? It's crazy. So what happens is, yeah, it looks like angular momentum is not conserved, but what's really happening is because this is connected by these stools and through friction to the ground and through the planet, the entire planet's rotation rate is slightly changed by this. But it's so small, right, we can't see it. And that's why, yeah, sure, if you could measure the change in the planet's rotation rate, you could do every problem with angular momentum. But in practice, that's not feasible. Now, I wouldn't be going over this unless it's a common test question. So the hidden angular momentum, or if you ever see a question on the test where I'm talking about this, and I'm like, it looks like angular momentum isn't conserved, but my teacher told me it was. What's the story? Usually it has to do with the entire planet. Do you know what I'm saying? Just keep that in the back of your mind on a test question. It'll appear somewhere, a test 3 or the final will ask about this. Hopefully you can remember that from the stupid discussion. So let's get back to here. All right. Is that enough? And this basically we did parts A and B here. We said, what is it and why? One of the tests that I've written, I don't remember which one it was, literally says, explain why we don't use angular momentum here. So one, I don't know if it's your class or the other class or both classes, this might be there. Just study it. Know it. Okay, C. What has to be true if we want to use conservation of energy? We'll call this C and D. What has to be true if we're going to use conservation of energy? Not torque external is 0, but something else equals 0. What was it? I want E initial equals E final. Usually I write down, oh, go ahead. What was that?
4, 6.
No. Work. Work. You're close. Right? Isn't it E initial plus work equals E final? We need the work to equal 0. And it's work external and non-conservative has to equal 0. Right? Now, in this case, when there's a collision, we've talked about this already today. When there's the collision taking place, do you lose energy? When we have this type of collision, this is a perfectly inelastic collision. Do you lose energy? Yeah. So do you agree? We know from experience, there's some external and non-conservative work during the collision. Okay. It's literally changing the macroscopic motion. You have to squeeze, you have to smash the Velcro or smash the clay or whatever, and the molecules themselves heat up and you lose some of that kinetic energy. So we know that E1 is not equal to E2 for perfectly, well, how about just for any inelastic collision? What about E2 and E3? Is it okay to use conservation of energy between stages 2 and 3? What problem does that look like? The problem from lab last week, right? A pendulum with a point mass on it, swinging upwards, and we did it with energy. Now, we got to be careful here. I'm assuming there's negligible friction at the pivot. I'm assuming air resistance is negligible. Probably not really true, but approximately true. Right? If you try to swing a meter stick through the air, you're going to get some air resistance. But we're going to assume E2 is equal to E3 if we ignore friction and air resistance. Right? And that makes the problem doable. So yeah, it's not going to be exactly right, but it should be pretty close. Sort of like this one wasn't exactly true, but it's going to be pretty close. We're so close to having all of them. I want to stick the other one on here too. Even though this isn't a question in the problem, let's add it in. I want to emphasize this was angular momentum. Now I want to talk about linear momentum. What's the equation for conservation of linear momentum? What is the symbol for linear momentum or just regular momentum? P. So what I'm asking is, can we use P initial equals P final? There's a collision over here, right? In this case, oh, sorry, I'm a little scatterbrained here. The condition for angular momentum was this. The condition for energy was this. What's the condition for momentum to be conserved? That's the force one. Well, what do you think? Is that true? Let's talk about during the collision. During the collision, do the external forces drop to zero or not? In particular, let's look at these two. The 3mg is going to be balanced by Ry, agreed? What about Rx? Is that balanced? No. Now think about this. Let me back this up a bit. Watch what happens when I punch a meter stick without a pivot. You agree it both translates and rotates? The pivot prevents the translation. The pivot, Rx, prevents momentum from being conserved. Angular momentum is still conserved because those pivot forces cause no torque. But linear momentum is not conserved. Yes?
So Rx points right that way. If it wasn't there, the torque would rotate that way.
That's right, that's right. So if I can hold this thing, right? Obviously, I'm sticking in a pivot here, but I'm trying to let go and I can't, so I'm just going to kind of slow-mo it, pretend this hand isn't here. When you punch it at the bottom, it started to tip back. The pivot, if I hold it right here, prevents it from tipping back. That pivot point, horizontal force, prevents the momentum from being conserved. Because it causes no torque, angular momentum is conserved. Good?
Yeah.
Yeah, and then again, depending whether you punch high or low, there it goes back, there it goes forwards, right? So in some cases, this force might point in a different direction, but whatever. In general, it's always there. If you care about baseball, the sweet spot in baseball happens to be, now think about this. If you punch it down here, the force is forwards. If you punch it up high, force is there. I think it's if you punch it right somewhere at the center of percussion, which I forget where that is. I think it's 2/3 of the way or something. But if you get it just right, you can punch it and you will not have a force at the top. And it will tend to not rotate. So I guess in that one weird case, you could have it be a conservation momentum problem. But yeah, if you hit a baseball really hard and you happen to be right at this one sweet spot, you won't feel a large force in your hand, right? But if you hit it too close to the bat or too far from the bat, you will feel this force in your hand. Or whatever. All right, enough on that. Okay. So now, let's go to part E. Why is the center of mass relevant? Come on now. Oh, am I on there? Okay. Why does the center of mass matter in this problem?
That's where it tends to rotate.
No. If it was in free space without a pivot, you're right. But this one has a pivot in it, so it's going to tend to rotate about the pivot. If you're wondering about the question you just asked, it's actually the very next problem. We redo this problem without a pivot and see the differences. Okay. All right. So it's going to rotate about the pivot. That's not why we need the center mass. Maybe I could help you out a little bit. Can you tell we're going to use an angular momentum equation to compare these two stages and a conservation of energy problem to compare these two stages? You can tell that's what we're going to do in a minute. Which one of those is going to need the center of mass? Do we need center of mass for the angular momentum? What's your gut tell you? Have we used it at all earlier today? Have we used center of mass earlier today in any of the problems? No. Why do we need center of mass for the energy problem? For the reference level for the frickin' height. Right? The center of mass height is what we need. We're going to need the height of the center of mass for the energy problem. That's why the center of mass matters. Is that helping? So this is the idea. If I throw a test question on your test that has something similar to this, which I've done pretty much every year since I've taught this class, either test 3 or the final or both, you got to know what to do. Here's the idea. Identify when you can use angular momentum and when you can use energy. Make sure you don't screw that up. Next, we're going to need to figure out the height of the center of mass because we're going to need to know that for doing the energy problem. Finally, write down all this crap, plug in some numbers, solve for something. That's the general strategy for success. You ready to do it? I'm going to do it on the other board. Or any questions about that? Does that kind of make sense? Let's do it. So I'm going to just redraw this. 1 to 2 angulon. We had a mass M, V, the rod was 2M, and D connected to the ceiling somehow. Over here, right? This thing is rotating. Some rate omega. I want to write down angular momentum in stage 1 equals angular momentum for stage 2. And just so I'm consistent, I'm going to call anything that's going this way the positive direction. That way I can account for my minus signs in here. And notice in this problem, everything's going in the positive direction. What is the initial angular momentum? What should I write down? It's a point mass. How do you get angular momentum for a point mass? It's that special trick that we use. M V times something. R perp. Excellent. The impact parameter. The final moment of inertia is going to be I omega. You with me? What is R perpendicular? Draw the line of motion. What is the perpendicular distance from the pivot to that line? What is the distance from the pivot to the line of motion that intersects it at a right angle? D in this case. Yeah. The rod length. Absolutely. So do you agree R perpendicular for this problem is just D? What is the moment of inertia? How do I get the moment of inertia? Absolutely. It's going to be I of the rod plus I of the point mass. Absolutely. What's the moment of inertia of the rod? Is it going to be using a 1/3 or a 1/12? 1/3. The pivot is at the end. The moment of inertia should be bigger than the pivot at the center. Right? The moment of inertia is always smallest if a pivot is at an object center. So 1/12 at the center, 1/3 at the end. Tell me what I'm going to do wrong here. Everybody watch this, please. Tell me what I do wrong here. What did I do wrong? The mass is 2m. This is like the part that everybody forgets, right? The rod mass is 2m. So, and I'm not trying to be mean to you guys. It's just sometimes by changing the mass or the distance, you can make the algebra so much easier on students. So sometimes I will change the mass to 3m to make that 3 cancel, right? But if you don't catch it, you just lose a lot of points. What's the moment of inertia of the point mass? About this pivot, What is it?
MX.
Mx squared. What's x? D. So out of all this, let's see, this is going to be 2/3 plus 3/3. This is 5/3. Mg squared. What drops out? M and a D. You're right. M and a D. So this M cancels that M. This D cancels one of those D's. And out of all of this, I know this is not very easy to see, so I'm going to write it up here. Omega equals, let's see, 3V over 5D. Take a second to confirm that. The 3 comes up top, the 5D goes down under. And then I'm going to actually write that down here as well. Everybody get that okay? So now, just because I'm on Zoom and I got to deal with the camera crap, I need to erase this one and I'm going to keep that one down there. You got it written down? Got it? Okay. All right. Now we're going to go 2 to 3. E initial equals E final. We've already talked about why it's valid. Right? We've already talked about we need to get the center of mass radius, which is going to be about right here. Whatever. My picture's not perfect. So let's maybe figure that out. Now check this out. Radius for the center of mass is going to equal radius for object rod plus mass of the rod plus radius for the point mass times mass of the point mass all over mass total. Agreed? When I do this, radius center mass, let's go through. What is the radius for the rod? What do I mean by this? Well, the center of the rod is right at the center. So radius of the rod, you go from the pivot to the rod center. That's going to be D over 2. Is everybody okay with that? And notice what's the mass of the rod in this problem? 2m. So there you can see probably why I chose the 2m. It makes this calculation a little easier. You can't make every calculation easy, though. It turns out they always suck. What's the radius to the point mass? The radius from the pivot to the point mass is D. What's the mass of the point mass? What's the total mass? 3m, right? Because you got a 2m plus a 3m. Out of all this, we're going to get md plus md over 3m. That's 2md. That's 2/3. Before moving on, is that reasonable? Is that what you expected? Kind of ish? Yeah.
Yeah.
He said a little bit lower than halfway. Well, 2/3, that's a little bit lower, 16% lower. Good. All right. So now I need to write the energy problem. I know. Got a meter sticks everywhere. You guys are more advanced than a few weeks ago. I'm going to try this out. What types of energy are we going to have in the initial state? In stage 2 here. Rotational. What about gravitational? Are we gonna have that? How much, what do we usually do with gravitational energy? We pick a reference level. What would be a convenient reference level for this problem? This would be height equals 0. So if we do that, would we have gravitational energy? And so that's what, you're right, we did. It just happens to be 0 if we're clever and choose that to be 0. You're good with that? But I agree with you. It is there. It just happens to be 0 if we pick a nice number. Okay. What about, there's no springs, screw it. We're done, right? Do you agree this should be, what's the initial energy equation? It's kinetic. What's the equation for it? Perfect. It's swinging motion, so I don't write 1/2 mv squared, I write 1/2 I omega squared. Perfect. In the final state, you come up to some max angle theta. How much rotational kinetic energy do you have at the max? 0. It comes to rest. What type of energy do we have? Gravitational. What's the equation for that in general? Now here's where we got to be careful. This is not the right mass. What mass do I need to use? 3m. I need to use mass total. And I need to use height of the center of mass. So if you use the total mass and the height of the center mass, we got it. Feeling good? Well, I think we know the moment of inertia from the previous problem. Wasn't that 5/3? Didn't we think, isn't that the moment of inertia right there? You see it? So we've got 1/2 of 5/3 md squared, because this height omega squared. What's the total mass? What's the total mass? 3m g. What's a good way to figure out the height of the center mass? You're on it. It's that result I told you to memorize because it happens too often, right? And I'm just getting the Zoom camera ready. You just said it right. It's the radius center mass times that 1 minus cosine angle to the vertical. Is that still on, Alan?
Yeah.
Right, thanks. Cool? Question?
Do we need to use 3m in our moment of inertia?
No. Remember, this accounted for both pieces right there. Do you remember that? Take a look right there. It was 1/3. There's the 2m, there's the m, and all together that worked out to some number. And think about it like this. If it was only the point mass, it would be 3md squared. But because some of the mass is closer than distance d away, it should be a little bit less than 3md squared. It is. It's about 2md squared. It's close to that, right? That's 1.67. So is that good enough? Yeah. Good question. All right. Crap. What's the radius of the center of mass? Oh, we have it right there. Yeah, right there. See it? Sorry, I forgot we did that already. All right. Let's clean some stuff up and cancel it. Woo! Does the mass drop? One of the D's drops, right? This 3 drops. Do you agree? And now I'm getting so lost, I'm going to rewrite before I get out of control. Okay? So I get 5/6 d omega squared equals, what was it? 2g 1 minus cos. this is a good time to reread the problem and figure out what the hell we're trying to solve for. Somewhere in there it says the goal is to get theta in terms of D, V, and G. Crap. I don't see any V's in here. How do I get the V involved? That's the whole point of that original result. We could get the V involved and we're good to go. So I'm going to plug that in. 5, 6, D. The omega was 3V over 5D, and we got to square that junk. We're going to get the job done. Solving this for theta is possible. Now, when I do this one, let's do some math. I have a feeling it turns out to be you see the answer written there?
Yeah.
And I worked it out earlier today. It does work out. What was it, 20 GD?
Yeah.
So that's the claim. The answer works out to this. You guys can move that stuff around. It's not that big a deal. What should we always do with any answer? Check the units. Well, what are the units of V squared? What are the units of GD? No units. That's what it's supposed to be. Looks good. You agree that the argument of a function should have no units? Okay. Now, to speed things up a little bit, I want to actually do a demonstration of this and make sure I'm not making crap up, right? We got the whole thing set up. And what I want to do here is go to 8. Screen 8. The mass of this golf ball is 47 grams. Okay. The mass of this meter stick is 77 plus a little bit for this wood. Now, most of this wood is close to the center here, so it's not all of it. It actually has a mass of 130 grams when you count the bearings and everything, but most of that weight is right here on the axis. So I'm going to just basically pad my stats a little bit and say the mass of the meter stick is about 80. Now, I want to point out, we're not exactly following the exact numbers here. Here, we said the golf ball should have exactly half the mass of the meter stick. That's only approximately true, but it's pretty close. Now, I'm going to release this thing from a ramp, and if you can see this here, am I on this screen right now?
Yeah.
Okay, it's about 25 centimeters off the ground. If you remember from last time, we could do, mgh equals 1 half mv squared plus 1 half I omega squared, and then convert the omega, right? Remember the rolling brace problem that we did last time? We could convert a height into a speed at the end. Now I did that, and I did the math, and I said for this height, I think it's actually pretty close to 26 centimeters to the center mass. I got about 1.9 meters per second for V. So just going back here, give me just a second here. Do me a favor, get out your calculator. Let's assume D is 1 meter and V is 1.9 meters per second. Punch it in and see what angle you get. Because that's the speed of the ball when it hits the bottom of the ramp. So 3 times 1.9 x squared divided by 20 divided by 9.8 and then divide by 1. Now I need to do 1 minus that answer, and then I need to do cosine inverse of that answer. And I got about 19 degrees. Did you get that? Okay. Still working it out. You ready? Oh, wait, I'll wait. What's that?
Camera.
Oh, thank you. Thank you. All right. Okay, that's pretty close to on there. All right, you get about 19 degrees? Good. Okay, so just watch it. I'll run it 2 or 3 times, and it's not gonna be perfect for reasons we've discussed. Is it close to 20? Let's run it one more time. Watch again. If you guys need to scoot over, do it. Walk over here for a sec. Look at it head on so you can see it. Try and get on axis. So stand right there. Ready? Oh, this problem went off the rails. Oh. All right, let me try again. Pretty close to 20? Good enough for government work? All right, now remember that, right, this wasn't exact because the golf ball isn't exactly half the mass of the meter stick. If you were crazy, which I am, you could try and think this through, and you could say, okay, what if this was actually 1.1 M, which is closer to the truth, right? Or maybe 1.15 M. And then you could rework the calculations and see how that should affect the angle and see if it fixes up some of the errors. Good enough? All right. Whew. Take a look at problem 11.9. 11.9. I'm going to let you read that for a second while I erase the board and get some space. Okay. 5. I'm not going to do this whole problem, but I want to sketch it out. What did I say? 11.9?
Yeah, look.
So it's the same problem without a pivot point. Deep in space. Is it the same masses too? Yeah, so for this one, I have the same mass. Okay. This is the initial state. And this is the final state. They're going to collide, stick together. And what should happen when they collide and stick together? Are they going to translate? Are they going to move left, right? Is the entire system going to keep moving to the right? What do you think?
Yeah.
Yes. Is it going to rotate? Yes. So what is the critical point? We're in free space now. Where's this thing going to rotate? I don't see a pivot point. Where will it rotate?
Center mass.
The center mass. Did we actually figure that out in the last problem? Don't we know the center mass was 2/3 d from the previous problem? Okay, so there's the center mass. Afterwards, I would model this as a velocity translational for the center of mass. And then which way is this thing going to rotate? Is it going to rotate out of the page or into the page? Is the rotation out of the page or is it into the page?
Now,
Out of the page. Okay. So now, what do we have to do? The steps involved would be figure out center of mass. Agreed? Now, we did that already, so I'm just going to write it. In this case, I'll call this distance y. Y would happen to equal 1/3 d because it's the same as what we just did. Is everybody okay with that? Do you agree we're going to need some moments of inertia? We need a moment of inertia. We're going to need the parallel axis theorem. It's going to be I of the rod plus I of the point mass. That's still true. But notice, is the rod 1/3 or 1/12? Which one is it? 1/3 or 1/12 in this figure?
112.
What's that?
112.
Neither. 1/12 is if it's at its center. 1/3 if it's at the end. This is neither one of those. Do you agree? That's why he was saying use the parallel axis. So I of the rod would equal 1/12 mass of the rod, which is 2m d squared. If this distance is d over 3, how much have we shifted from the rod center of mass, which is at d over 2? What's the difference between those? Figure not to scale.
6.
Yeah, so this distance would be d over 6. 3/6 minus 2/6 equals 1/6. Sorry, it's not to scale. So then we'd have to do, what's the term for the parallel axis theorem? Mass times distance squared. What's the mass I should use for the rod? 2m. What's the distance the axis shifted? Is it d over 2, d over 6, or d over 3? D over 6 squared. Got it? What's I of the point mass? What's the equation in general? Mx squared. What's x? The distance between what and what? In this figure, what is x for the point mass? What's that? D over 3. So in this weird case, x equals y. Whatever. What mass should I use? M or 2m? M, because the point mass was just m. So notice in this one, the rod had 2m. You just got, okay, fine. You can add all that crap up and get the moment of inertia, right? Punch that crap into a calculator and use decimals. Don't try to do all the fractions. When I did your answer key for your test, I was using decimals too. It's just easier. Right? If you want to do the fractions, do it. That's cool. If you don't, use decimals. All right. Now what are we going to do? I've got 3 questions. Is momentum conserved? Linear momentum, yes or no? Yeah. These are the only 2 objects that are out in deep space. Ball exerts force on rod, rod exerts force on ball, but there's no other external forces. We could use it. So the short answer is yes. Is E initial equal to E final for this problem? Yes or no? What type of collision? Perfectly inelastic. No. We have an inelastic collision. Energy lost to deformation, I'm going to say. Anytime, this is why bumpers are designed on cars to crumple, right? If the bumper crumples during impact, your bumper gets destroyed, but not your skull, right? That's the idea, is hopefully parts of the car get destroyed, which is cheaper to replace than you. All right. Is angular momentum conserved here? What's your gut say? Yeah, we're in chapter 11. It's got to be. But what's a better way to say that? No external torque. So what do I write down? I need two more equations, right? I could say P initial equals P final. That's going to help me figure out velocity of the center mass. And then I could do, now be careful here. I just want to point something out. At the end, you could view the mass as 3m with this v, right? So your momentum equation is actually going to look like mv equals 3m times v center mass final. Does that make sense? Basically, the final velocity gets cut by a third. The angular momentum, we got to do m v r perp equals I omega final. What is R perp? What is the impact parameter? Nope. What is the impact parameter? D over 3 in this problem. It's the distance from the pivot point. Well, the pivot point is the center mass. I know it's time to go, but just hang in there. And I is this junk. We got it. Do you agree this is a trivial problem? You can do this. The trick is you got to make sure you practice a couple of these before you start doing the practice test. So you get used to this annoying factor of basically each new problem, what changes. There's only so many I give. The ones that I gave you today are going to look similar to the test questions, except I might change a mass to 4m just to see if you could redo the math and you can't just memorize the answer. You know what I'm saying? And so it's usually pretty obvious. If you follow all the work and you put in the wrong mass, it's usually easy to follow your work and you can usually get some partial credit. But you got to know how to do the steps. All right. So a couple of things in closing. I didn't have time to do all of them. Let's say it like this. Make sure you do 11.11. That's one we didn't get to. I actually like 10A and 10B, but I wouldn't spend time on those at home. We could talk about that. Maybe I'll show you a video tomorrow in lab. I really like 11.nasty at the bottom 89. 11.11 and 111. It's really hard. I'm not going to lie. And yet you can do it. Alan, do you remember that problem?
Yeah, I definitely do.
Did you learn something from it or not?
Yeah, I got really close to solving it. So there's that formula, right? I don't want to say too much, but there's that formula at the end. I just didn't know I was supposed to do that.
Yeah. Oh,
It's a really good question.
there's a lot. It's basically everything we've been doing today, but with a weird object that's not a rod. So you have to really know what you're doing. You have to get the parallel axis theorem right. So there's a lot. Yeah. Try it. If you fail horribly, follow through the solution and at least learn from that problem. Got it? All right. Page 91 talks about the magic wheel. Remember the wheel we had that was floating there? All right. You can read about that. There's YouTube videos, 11.16. I already mentioned these problems. Look on page 93 really quick. 93. I mentioned I would say something about it. This is the time. I've got just enough. If you look at page 93, 94, 95, 96, and 97, it looks like way too many problems to do. It is. However, the questions I ask basically are, can you use conservation momentum, energy, or not? Can you use conservation of angular momentum? Can you use conservation of linear momentum? So the idea with those problems is if you're wanting some extra practice with problem identification, you look at these problems and say, okay, if he gave me these problem statements, which rules apply? And then you check that, and then you don't do the problem. You just see which equation should be valid for each of these types of problems, and you can do it rapid fire. So it's not nearly as intimidating as it looks. The answers might surprise you for one or two, but most of them are straightforward. Got it? And now I need a volunteer for one last demo on the way out the door. What is it? This one? 7? Okay. I have a perfectly normal suitcase here, and I need someone to carry it for me. So we're right here. You guys are in the frame. I don't know if you want to move or not. I swear there's nothing unusual about this suitcase. Alan, can you see me on the screen here or not?
Yeah.
Okay. You might just want to jump around to the other side of the table there. I swear this is a perfectly normal suitcase. Nothing weird here. Nothing up my sleeve. I'm gonna need somebody over here pretty soon. Okay. And then just stand right in front of me there, right over there. Yeah. Yeah. Nothing unusual in this suitcase at all. Broke that one. I swear there's nothing weird in here. Oh gosh. Now what I need you to do is walk forward 3 steps and turn and go through the door. Be careful. Now turn. Whoa, whoa, yeah. Why isn't it able to turn? Let's show them here. Come over here. So the idea, is this crazy? It's like if you try to turn, right? Ah! Let's look what's inside. Oh, jeez. These are the things that my students make for me. Perfectly normal suitcase. It's a 45-pound flywheel. Isn't that stupid? All right, let's call that a day. Let's give him a round of applause here. Secret suitcase is one of the problems in the workbook. I think it's 11.14. If you're curious. So dumb. Oh my gosh, a student made that. That's pretty amazing.